Hi, in this video we are going to discuss Parseval's identity in Fourier series, which is a very important result. Now first let us start with a periodic signal. X of t is a periodic signal with fundamental period capital T0. Okay, so x of t will have the Fourier series representation, k running from minus infinity to plus infinity, ak, the Fourier coefficients, and we have the complex exponential signals e to jk omega 0 t. Here omega 0 is related to t0 by means of this relation. Okay, now x of t is a signal which can be expressed in terms of a Fourier series given by this expression. Now, what can we say about the product of x of t and x conjugate of t? This is interpreted as the instantaneous power of x of t. So at a particular time instant, x of t times x conjugate of t. So here this star denotes complex conjugate. Okay. So, by definition, x of t times x conjugate of t is the instantaneous power at a particular time instant. Now, if we integrate the instantaneous power over a period, so from an arbitrary t0 up to t0 plus capital T0, we integrate the instantaneous power, and this is the energy of x of t over a period. Okay. So the Parseval's identity will be an identity relating this quantity to the Fourier coefficients. Now, how can we obtain such a relationship? Of course, we can substitute x of t, the Fourier series representation of x of t, in this expression. So, okay, now this expression can be written as from t0 to t0 plus capital T0. Okay, the Fourier series representation of x of t, k from minus infinity to plus infinity, ak, e to jk omega 0 t. So let me put a bracket here. And then we have x of t conjugate. Now in this product, we are going to multiply the series expressions term by term. Therefore, it will be convenient to use a different index here, say m, from minus infinity to plus infinity, a sub m e to j m omega 0 t, and we have now the complex conjugate of this expression integrated with respect to t. Okay. Now, I think it is clear why we have chosen a different index in the second series expression, where we evaluate the conjugate of x of t, because we have to keep track of the terms of the product when we multiply these two series expressions term by term. Okay, now this expression can be written as follows. Now, omitting some technical details, we can interchange the series expansions and the integration. So we have the series k from minus infinity to plus infinity and m from minus infinity to plus infinity, ak. Now the conjugate of this series will be the conjugate of each term. The series composed of the conjugate of each term. So we have am conjugate, and then we have the integral from t0 to t0 plus capital T0 e to j k omega 0 t and e to minus j m omega 0 t integrated with respect to t. Okay, this minus sign is coming from the conjugate of e to j m omega 0 t. Okay, the integral. Okay, let us just look at the integral from t0 to t0 plus capital T0, the integral of e to j. Now we can combine the two expressions as k minus L, not L, but M. Okay, M omega 0 t integrated with respect to t. Okay, so this integral is 0 for m different from k, and it is equal to t0 for m equal to k. It is very easy to see why, because if m is different from k, here we have an integer multiple of omega 0, and omega 0 is 2 pi over t0, remember. So we integrate, therefore, this expression over a period, and this is a periodic expression with a period equal to t0. Therefore, its integral over a period will be equal to 0. However, if m is equal to k, this will be equal to 0, and the integral will be t0. Okay, and now this series expression becomes, okay, let us write down the integral again. So this integral from t0 to t0 plus capital T0, x of t, x conjugate of t, integrated with respect to t, is equal to. Now, since the integral of the complex exponential term is equal to 0 for m different from k, the double series expression will reduce to a single series, k from minus infinity to plus infinity, ak, and we have only a non-zero result when m is equal to k, therefore we have ak conjugate. Multiplied by t0. And that t0 can be written on the or transferred to the left-hand side of the equation as 1 over t0. Okay, so this expression is called Parseval's identity or Parseval's relation. Parseval's identity. And we can also write it as follows. Remember that when you multiply a complex quantity by its conjugate, we get modulus square. So, equivalently, we have the expression which is equivalent to this original expression as follows. We have modulus of x of t squared integrated, and on the right hand side, k from minus infinity to plus infinity, modulus of ak square. Okay. Now, remember we have interpreted x of t times x conjugate of t as the instantaneous power. So if we look at the left-hand side of Parseval's identity, we see the integral of instantaneous power over a period divided by the period itself. Therefore, this is just average power of x of t over a period. Okay. Now, Parseval's identity is interesting. Since we have an equality, the left-hand side is equal to the right-hand side, obviously. So, the left-hand side interpreted as average power of x of t over a period by means of this integration with respect to t over a period. The right-hand side is also average power of x of t over a period, now calculated in terms of the Fourier coefficients. Okay, so we can now see an example to see an application of Parseval's identity. Okay, the example we are going to see will be the periodic pulse train example. So we have repeated this in the previous videos. So we have this pulse signal P of t, which is equal to A in the interval from minus t cap over 2 to t cap over 2, and we obtain x of t as the periodic extension of this P of t, k, or let us use the index m running from minus infinity to plus infinity, P of t minus m capital T0. Just to avoid overlaps, T0 is chosen to be greater than T cap. T cap is, as you see, the duration of the pulse, and T0 is our fundamental period. So x of t will have a Fourier series representation, and the Fourier coefficients are, we have obtained this expression in another video. So it is a t cap over T0 sinc of k t cap over T0. Okay, if you wish, we can write down the expression of sinc just to remember what we mean by the sinc function. It is sine k pi t cap over T0 divided by k pi t cap over T0. Now, Parseval's identity tells us the following. Over 1 over T0, if we integrate over a period, say from minus T0 over 2 to T0 over 2, x of t modulus squared integrated with respect to t. Remember that we have obtained the Parseval's identity for the general case where x of t is a complex valued signal, but for the real valued signal, of course, magnitude x of t squared will be equal to x squared in this case. So this is equal to, by Parseval's identity, k from minus infinity to plus infinity, ak modulus squared. Also, we see in this case that AKs are also real valued. So, in general, the coefficients are complex valued, but for this case, they turn out to be real valued. So, in this case, we are going to have the square of AKs simply. Now, the integral 1 over T0 from minus T0 over 2 to T0 over 2 x square of t. Now I can write it in this form because we have the real valued signal is equal to 1 over T0. The integrand is non-zero only from minus t cap over 2 to t cap over 2, where it is equal to a squared. Okay, therefore this will be equal to a squared t cap over T0. Okay. Therefore, by Parseval's identity, a squared t cap over T0 is equal to k from minus infinity to plus infinity. Now the square of the coefficients, because the coefficients are real valued, therefore we can take the squares. Otherwise, if the coefficients are complex valued, then you have to take the modulus first and then the square. Okay, so we have a square t cap square divided by t0 square and sinc square k t cap over t0. Okay, so this is an application related to the Parseval's identity in Fourier series. Thanks for watching.